Well, so we discussed in our last lecture the normal curvature, in fact the principal curvatures. So, the maximum and minimum values of the normal curvature are called the principal curvature. We denoted the principal curvature by the symbol K1 and K2, and these are principal curvatures. And definition wise, they are the maximum and minimum values of the normal curvature K. Now, one can think of curves over a surface whose normal curvature are K1 and K2. These curves are called the lines of curvature, and the tangent to these curves are called the principal directions. So, principal directions are nothing but the tangent to the lines of curvature. So, we will work out the equation of the lines of curvature and principal directions. So, first of all, let me write down the definitions for these lines of curvature and the principal directions. The two directions, the two curves on a surface through a point P, whose normal curvatures through a point P, whose normal curvatures at P are the principal curvatures. Two curves on a surface through a point P whose normal curvature at P are the principal curvatures are called lines of curvature. And the tangent to the lines of curvature are called the principal directions. The tangents to the lines of curvature are called principal directions. So, first of all, we will work out the equation of the lines of curvature and principal direction, and then we will think of the existence of lines of curvature and principal directions. Well, you can realize them if you have a right circular cylinder. Then these two directions, the tangents, if you draw tangent in this manner to the base curve, then this direction is a principal direction. Here the curvature you can see is 1 upon a square. I am taking right circular cylinder. Similarly, if you draw the tangent to this straight line, then it is also, this straight line is also one of the lines of curvature, and the normal curvature is 0 over here. So, and here it is maximum, it is 1 upon a. If the radius is a. All right. Similarly, you can think of the lines of curvature on other surfaces also. So, the equation of lines of curvature. And the same equation will work for the principal direction also, lines of curvature and principal directions. If you remember, we had one expression for the normal curvature. So, we know that while working out a quadratic equation for normal curvature, we found that Kn equal to B11 plus B12 lambda upon G11 plus G12 lambda, and that is equal to B12 plus B22 lambda upon G12 plus G22 lambda. If you consider the cross product of these two terms, you will get an expression in terms of lambda. You keep Kn away, just look at these two values of Kn. So, this gives the following. I am multiplying cross G12 plus G22 lambda into B11 plus B12 lambda minus G11 plus G12 lambda into B12 plus B22 lambda equal to 0. So, if I simplify this equation, I will get a quadratic equation in lambda. So, lambda we know should keep in mind that lambda is a direction. It is du2 over du1. And we arrive at this expression when we have assumed that derivative of Kn with respect to lambda is 0. So, that means this direction is actually the principal direction. If you consider this expression of Kn, then lambda is actually a principal direction. All right. Now, if I simplify it, I will be getting a quadratic equation. So, after simplification, this equation becomes, after simplification, I will be getting G12 into B22, G12 into B22 minus B minus G22 into B12 lambda square, and then plus G11 into B22 minus G22 into B11 lambda, and plus G11 into B12 minus G12 into B11 equal to 0. So, this is an equation in quadratic equation in lambda square, and this will give me the two values of lambda, means the two principal directions. I can rewrite this, can be written here. Lambda I have already mentioned is du2 over du1. So, if I put d in place of lambda du2 over du1, it will become G12 to G12 B22 minus G22 B12 into du2 square plus g11 b22 minus g22 b11 into du1 du2. I have multiplied throughout by du1 square as well, and the last term here is g11 into b12 minus g12 into b11 du1 square equal to 0. You can see that this can be written in a very simple manner as a determinant. So, this looks like du2 square minus du1 du2 and du1 square equal to 0. Here it will be g11, g12, g22, b11, b12 and b22. This equals to 0. This is a expression which is simple to remember and very symmetric. You can see that I have written it correctly or not. du2 square is g12 into b22, g1 minus g22 into b12. Similarly, other terms also you can check it out. So, this is known as the equation of principal direction as well as the lines of curvature. This is the equation of, this is the equation of lines of curvature. In fact, it is a differential equation, lines of curvature as well as principal directions. Okay. And now about the existence of lines of curvature over a regular surface. So, for the existence we have a theorem which says that on a regular surface you can find out two lines of curvature passing through a given point which are orthogonal to each other. So, this is interesting. From every point there will pass two lines of curvature which will be orthogonal to each other. In case of a cylinder, you have just seen that from every point there passes a circle as well as a line. So, this happens on all regular surfaces. Okay, so, this is the theorem that I will be discussing now. With regard to the existence, I have this theorem, let me call it theorem number 1 for lines of curvature. From any point of a surface, from any point of a surface, there pass two lines of curvature which are perpendicular to each other, Okay. Proof is easy. What we will be doing, we will assume that the two directions are du1 upon du2 and delta u1 upon delta u2. You can rewrite down this above equation as follows. So, the equation of the principal direction and lines of curvature can also be written as G11 into B12 G11 into B12 minus G12 into B11 into du1 upon du2 square, okay, and then plus G11 into B22 minus G22 into B11 du1 upon du2, and then plus G12 into B22 minus G22 into B12, okay. So, the differential equation for lines of curvature can be written as now suppose the two principal directions are du1 upon du2 and delta u1 upon the two roots of this. So, these two roots you can understand are nothing but the two principal directions. Suppose the two principal directions PD I am writing. The two principal directions are du1 over du2 and delta u1 upon delta u2. Okay. So, if these are the two principal directions, I can look at the sum of the two directions, that will be the du1 upon du2 plus delta u2 upon delta u2. It will be minus times this upon this. So, it will be G22 B11 minus G11 B22 upon this one G11 B12 minus G12 B11, and the product of the principal directions is du1 over du2 delta u1 over delta u2. This is G12 B22 minus G22 B12 upon G11 B12 minus G12 into B11. All right. So, you can understand what I am going to do. In fact, I know under what conditions the two directions over a surface are orthogonal. The condition, if you recall, is that G11 into the product of the directions plus G12 into the sum of the direction plus G22 must be 0. So, this is what I am going to check, whether this condition holds for the two directions or not. If it holds, I will say yes, it is a true statement. So, now consider the orthogonality condition. So, consider the orthogonality condition. This condition, let me recall, is G11 into the product of the two directions plus G12 into the sum of the directions plus G22. So, we will check it up whether this is equal to 0 or not. So, this is equal to G11 into this one product G12 B22 G12 B22 minus G22 B12 upon G11 into B12 minus G12 into B11 plus G12 into sum G22 B11. Have we taken care of the minus sign? Yes. Okay. Okay. G22 B11 minus G11 B22 upon G11 into B12 minus G12 into B11 plus G22. Okay, we have this must be 0. I will show this. So, I have just considered the left hand side. If turns out to be 0, we are done. Okay, I am just seeing whether it is going to become 0 or not. G11 into G12 B22 minus G11 G22 B12 plus okay G12 G22 B11 minus G11 G12 B22 and plus okay plus G22 into G11 B12 minus G12 G22 B11. First and fourth are cancelled out. G11 G22 G11 G22, yes, these two terms are cancelled out. G12 G22 B11. So, the answer is here. So, in fact, we verified the orthogonality condition. So, we concluded that these two principal directions are in fact orthogonal to each other. So, this proves the statement. So, what has happened over here? The orthogonality condition holds. This implies the orthogonality condition for principal direction hold, proving the assertion. That proves our assertion. That proves. Yes. From every point we can find two lines of curvature which are perpendicular to each other. Their K1, K2. Their curvatures are K1, K2. Normal curvature. That proves the assertion. Also, it is a geometric property which we have verified through our computation. Okay. Now, the next theorem is also interesting, which says the lines of curvature are parametric curves. In fact, we already have the notion of parametric curves, and these new curves have appeared as lines of curvature. So, we would like to see whether under what condition the lines of curvature and parametric curves are same. In fact, this will be a facility for us. We can always choose our lines of curvature as parametric curve. So, that will make our computation easier all the time. So, let us see what is the condition for this to happen. So, let me write down the statement which I am going to prove. This is theorem number. No, no, they may not be lines of curvature. No, no, there are conditions. This is theorem number 2. The lines of curvature are parametric curves. The lines of curvature are parametric curves if and only if G12 as well as B12 both are 0. B12 should also be 0. Parametric curves are orthogonal if G12 is 0. And if parametric curves becomes lines of curvature also orthogonal, then B12 should also be 0. So, we have a stronger no, both. So, the proof will follow from the differential equation that we just had. Let me write down somewhere over here the equation du2 square first minus du1 du2 and then du1 square. Here we have G11, here you have G12 and this is G22, B11, B12, B22. This is equal to 0. This is the equation for lines of curvature and principal direction. Okay. So, we already know from the last theorem that there pass two lines of curvature which are orthogonal to each other. If we take them as parametric curves, so from the last theorem, from theorem 1 in fact, we know that there pass two lines of curvature from every point. There pass from a given point two lines of curvature which are perpendicular. Now, geometrically you can easily realize that if you have got hold of two curves on a surface, from every point you have got a pair of curves which are orthogonal to each other, then you can work out with your parameter so that these two curves become parametric curves. So, it is always possible. So, we can assume these curves as parametric curves. Yes. So, if they are taken as parametric curves, if these lines are taken as parametric curves, yes, then G12 must be 0. Yes, then we know that G12 becomes 0. This is number 1. The parametric curves are orthogonal if and only if G12 0. So, now what is the differential equation of parametric curves? U1 equal to constant gives you U2 curves. So, that means du2 will become 0, du1 equal to 0. So, for U1 curves du2 is 0. So, for U1 curves u2 is constant, and that means du2 is 0. Now, put du2 equal to 0 over here in this equation, and g12 also equal to 0. So, what this will equation, if I call this equation as equation star. So, from star we get, using this thing, from star we get. So, this becomes 0, okay. du2 will make this 0 and this 0. So, du1 equal du1 into what? g11 b12 minus b11 g12. So, this will give you g11 into b12 equal to 0. So, g11 into b12 equal to 0. Am I right? This is number 2, sorry. Okay. If you look at the other parametric curves or other line of curvature, that is now u2 curve. For u2 curve, du1 is 0. So, put du1 equal to 0, g12 is already 0. So, when du1 0 will make this 0 and this 0. So, together with du2 square you will be getting this into this minus this into this. This is already 0. So, g22 into b12 is 0. g22 into b12. This is number 3. Okay. g22 into b12. ठीक, okay. Now, our surface is all the time assumed to be regular, and therefore, g cannot be 0. And this time g is simply g11 into g22. So, as g is positive on a regular surface, so what will happen? g11 into g22 will become positive, and this means neither g11 nor g22 is 0. So, this implies that g11 is non-zero as well as g22 is non-zero. So, if you look at relation number 2, here g11 is not 0, b12 is not 0, g22 is also not 0 from 3. So, b12 is 0. So, that non-zeroness of g11 and g22 will give you that b12 is 0. So, using the above, information, what do 2 and 3 imply? 2 as well as 3 imply that b12 equal to 0. So, you have got both g12 as well as b12 0. So, one way we have proved. Okay. So, if our lines of curvature are parametric curves, then g12 and b12 is 0, orthogonal also. If the lines of curvature are parametric curve, if and only if g12 and b12 is 0. Now, conversely, if you have only g12 and b12 are 0, you are given, then you should show that these curves along which these two things are 0 are nothing but parametric curve and as well as lines of curvature. So, conversely, if g12 and B12 are 0, then from star once again, then star gives us, what star will give you? Put G12 equal to 0 as well as B12 equal to 0. So, you will be getting with du2 this both are 0, so is 0. With du1 du2, with this also you will get 0, only du1 into du2 du1 into du2 multiplied by G11 into B22 minus B11 into G22 equal to 0, because the right side here is 0. Okay. And this implies that du1 into du2 is 0. This you do not expect to be 0 all the time, because these are the quantities which are not in your hand, they are invariants of the surface. Okay. So, what is 0 is du1 into du2. So, this I will say is the differential equation of parametric curves. This gives you what? Du1 equal to 0 or du2 equal to 0. du1 equal to 0 means u2 curve, du2 equal to 0 means u1 curve. So, this is the equation of parametric curves. This is the equation of no, it is possible, but you see you are along the curves and you cannot make any changes over there. So, you have to see what are the invariants of the curves. So, these du1, du2 are the things which are related to curve. Why I am saying u1, u2 are the parameter of the surface, but when u1 becomes a function of u2 or u1, u2 both becomes function of a parameter, so that means you are travelling along a curve. Okay. So, this is the equation of parametric curves. All right. So, this proves theorem number 2 also. So, these two theorems 1 and 2 tell you what is the relationship between lines of curvature and parametric curve, and you can choose lines of curvature as parametric curves also. All right. So, the last theorem, I will do this last theorem after a break of 5 minutes. Okay. So,